And we're going to kind of leave evolution here for 2 lessons, and then we'll jump back into it. We're kind of using a scenario, an idea that of how did rabbits grow so quickly in Australia, and they just absolutely exploded there. The idea behind this is that populations grow in an exponential way if they have no limitations, rather than linear. We kind of tend to think of growth as being linear. It's kind of our natural thing, right? Where the increase is consistent like this. But in populations, we can have the growth rate remain constant. In this case, the growth rate would be 0.5. That growth rate can remain constant, but because as we add more are having babies, we get this kind of growth, right? We get a curve to it. And so that's exponential growth. And that's what happened with these rabbits in Australia. Really quick, let's just go over the formulas here, okay? Our first one is growth rate. So we take our generation 1 and subtract our generation 0 and divide by generation 0. Most common mistake on this type of question would be to do generation 1 minus generation 0 divided by generation 1. We want to see how much the starting population grew. That's what we want to see. We don't care how much it grew compared to what it became. We care how much it grew, the population that was actually doing the growing. So if we were going to do this question here, let's see if I can get this open again. Okay. We take our next generation, which was 18, our current generation, which was 10. We do 18 minus 10, and we subtract that to get 8, and we divide it by 10. So our growth rate would be 0.8. So that's what this is showing us. Our growth rate would be 0.8. All right. Well, if we want to figure that out, like how that growth would occur, we take that 10 and we multiply it by the 0.8. That's the percentage that should reproduce each time, right? And so 10 times 0.8 would be 8. And then we add it to what we have, which is 10. So we get 18. That's what you're seeing. What's wrong with it there? I'm sorry. That's what we're seeing here. And this is our exponential growth formula. We take our current generation and times it by R. So 10 times 0.8. And then we add it to our current generation. There's other ways to do this. You can do 10 times 1.8. Lots of different ways to format this. I like to do it this way because it shows each part as being distinct. Whatever works for you is fine. Just make sure that you understand why you're doing it. So 10 times 0.8 gets us that 8. We add it to that 10, and that gives us to our next generation. We predict will be 18. Then we go from there. 18 times 0.8, times it by the growth rate again. That gets us to 14.4. We add that to 18. So 14 plus 18 gets us to 32. And then the next time we do 32 times 0.8, and we add that to 32. And that's how we go through stepwise and do this. Again, this is a periodic growth model that we're doing here. Some organisms do grow that way. Other organisms, a continuous growth model would be better. We're trying to keep the math really simple. And so we're not going to worry about continuous growth models. Please use this periodic growth model. It is less accurate for a lot of species, including humans. But we're trying to understand the components that go into it. And so I'm just going to ask that you do it this way rather than another way that you may be familiar with. Though it is probably more accurate in most cases, but not when we have periodic growth. So as we go through, what you should have seen is that our model, our exponential growth model, stinks. It predicted the population to be way bigger than it actually turned out to be. So what went wrong? Why were we getting too many individuals added to our population? Well, it's because in real life, you can't just have a population growing exponentially. There's a limit to that, and that gets us to our next lesson.